All right, welcome to a video on lesson 38. The topic of the lesson is using properties of equality to solve equations. We have done some solving of equations up until this point. An example of the types of equations that we've solved would look something like this. Let's just say we had maybe 15 minus x equals 9. And you would be asked to find x, but you were asked to do it using mental math. Of course, you just ask yourself, what number do you take away from 15 to get 9? And you come up with x equals 6. All right. Another example, maybe you had something like x squared plus 16 equals 25. And you ask yourself, what could I square? What do I need to square here? And then add 16 to it in order to get 25. But again, it was a mental math problem. And since the numbers are orchestrated very neatly, it was easy to come up with those solutions because you could just think through your multiplication rules in your head and come up with the answer. In this case, if you take 3 and you square it, you get 9, and 9 plus 16 is 25. So x would have to be 3. All right, so they were just mental math problems, and they were fairly basic. But the truth is, the best way to solve equations is not by using mental math. It's instead by using what we call an algorithm. And an algorithm is a process. I'm going to make that red so that we can use it as a definition word. This is a process for finding a solution. All right, and the process for finding a solution for when our objective is to find the solution of an equation, finding a solution of something like this or like this, our process is to use what we call inverse operations. Inverse operations. All right, and we're still solving basic equations at this point, but the inverse operations are fairly straightforward. The inverse operation of addition is subtraction. The inverse operation of division is multiplication. And the inverse operation of multiplication is division. The inverse operation of subtraction is addition. So in other words, the opposite operation. The word inverse really is representative of the word opposite in this case. All right, so if I were to take an equation like the first one, ignore this operations of properties of equality for a moment, but if I were to take an equation like this first one that we dealt with, let me recopy that and bring it down here. We know the answer is 6 because of mental math, but if I were following an algorithm here, then the first thing I would do is recognize that my job is to solve for x. The way we word this is we say we need to isolate x. That means get x by itself. Isolate the variable. And if we're trying to get x by itself, then we need to move everything that's around x, everything that's on the left side of the equal sign here, away from it. We need to get this x standing still. Nothing else can be on the left side of the equation. And in order to do that, we're going to use an inverse operation. If I have this 15 hanging out over here, well, I want to get rid of it. So how do I get rid of 15? I add the opposite of it. If it's a positive 15, well, if I add a negative 15, or instead just subtract 15, well, now that it's gone. It disappears. And what am I left with on the left side of the equation? Negative x. But the problem is this. Equations have to have equality. They have to be balanced. If I do something to one side of an equation, by mandate, I must do the same thing to the other side of the equation. And therein lies the whole foundational concept of solving equations in mathematics, particularly algebraic equations. You must treat both sides of the equal sign the same. So if I subtract 15 over here just because I want to get x more isolated, then I have to subtract 15 from the other side. I have to. That's what we call our properties of equality. So the operation properties of equality say that if I have two things set equal to each other, then if I add something to one side, I have to add it to the other side. If I have two things equal to each other, then if I subtract something from one side, I have to subtract it from the other side. If I have two things equal, if I multiply by something on one side, I must multiply by the same thing on the other side. And again, if I have two things that are equal, and I divide by something on one side of the equal sign, I must divide by something on the other side. The only way to keep the equations balanced is to use the same operation on both sides of the equal sign. So think of your equal sign as kind of your separator between the left side and the right side. If you do something to the left, you have to do it to the right. If you do something to the right, you have to do the same thing to the left. All right. Just one little note here. It says that as long as C is not 0, and that's just because we can't divide by 0, right? All right. So in this example that I started out with, if I subtract 15 from the left, then I have to subtract 15 from the right. And then I'm stuck with this little math problem. What is 9 minus 15? Well, you're basically adding, or you could say you're subtracting. You're doing your operation is, I'll write it out, it's 9 plus negative 15. Well, our rules for addition say that when you're adding two signs that are not the same, you subtract the smaller one from the larger. So I'm going to take 9 from 15 and get 6, and then I keep the sign of the larger, so negative 6, right? Only we knew the answer was positive 6 because we did it mentally a little earlier. And how do we reconcile that with our example down here? Well, if the negative of x, the negative of x is negative 6, well, that must mean that x is 6. It's the only way that works. Or, if you don't like that logic, and a lot of students don't, then you could say, okay, well, negative of x is the same as negative 1 times x. That's negative 1x, so I can divide by negative 1. If I divide by negative 1 on the left, I get positive x, because a negative divided by a negative is a positive. But if I divide by negative 1 on the left, I got to divide by negative 1 on the right. So negative 6 divided by negative 1 leaves me with positive 6, which we knew was the answer from the start because we started out by doing this problem just mentally. All right, so x must be 6. And instead of mentally working my way through it, which I would still recommend for a problem like this, it's basic enough for you to use just mentally use mental math to do it. Instead of using mental math, though, we used an algorithm. The algorithm says use inverse operations to step by step get your variable by itself. Get the variable to the point where it's just one x, just x, a single x, not negative x, not x plus 10, not 15 minus x. You can only have x. All right? That was a very basic example because, again, we could have done it mentally. The problems in this unit are not so basic. The problems take us to, I'm going to call this officially example 1, even though I've already given you 2 examples. The problems in this unit are designed so that you cannot do them so easily just using mental math. Stuff like x plus 1/2 equals 3/4. Now, to be honest with you, this one's not so bad. I would hope that some of you, a good portion of the class, if not everybody in the class, can look at a problem like this and go, oh, I'm pretty sure x has to be blank. Because you've all played around with quarters, you've all played around with money. You know that if you have a half of a dollar, 50 cents, and you add one more quarter to it, you're going to have 3/4 of a dollar, 75 cents. So x must be 1/4, right? I said it out loud, but I haven't written it down. X must be 1/4. But the truth is, if I use inverse operations, if I use my subtraction property of equality, then all I have to do is subtract 1/2 from both sides, and x would be by itself. The 1/2 minus 1/2 on the left, 1/2 minus 1/2 is 0. So that disappears, and I'm left with just simply x on the left side. So I've isolated my variable, but I still have a little math to do. Well, that's not so bad. We can do this math. We just have to find a common denominator. So I'm going to multiply by 2 over 2. So that gives me a negative 2 over 4 for this negative 1/2 fraction. And then I had this positive 3 over 4 Well, 3 over 4 minus 2 over 4 is 1 over 4. And so, as we said, the answer is in fact 1/4. All right? But instead of just doing it mentally, we actually showed the algorithm. We showed the mathematical process, which was, since we had x plus a half, I simply subtracted a half from both sides so that I can get rid of the half. All right, let's try another. What if it's, let's say, a decimal? X minus 1.3 equals 4.2. You can sit here and think in your head, well, what number do I have to subtract 1.3 from in order to get 4.2? It's obviously going to have to be bigger than 4.2 because I'm subtracting 1.3 and then I'm getting 4.2 as an answer. So this number x is, I don't know, 5 point something, right? Well, it doesn't have to be a guessing game. It doesn't have to be mental math. If we have minus 1.3 here, then I need to add 1.3 to clear it off. I'm going to use the inverse operation. This is a minus, so I'm going to add. And that cancels the 1.3 out. But since I added 1.3 on the left, I'm going to have to add 1.3 on the right. And very easily, x has to equal 4.2 plus 1.3, which is 5.5. Final answer. Again, still not difficult. We could have probably handled that in our heads. All right, not too tough yet. So let's step it up a notch. What if we had 1.2 is equal to x over 4. 1.2 is equal to x divided by 4. All right, so now we've got a fraction over on the right and we've got a decimal on the left. We're kind of mixing things up. It's still not a terribly complicated equation, believe me, but it's a little harder. We've got a little bit more going on. All we have to do, again, is focus on our variable. I want x by itself. I want to get x isolated. In order to do that, I have to get rid of this 4. Well, where's the 4 coming into play? It's divided into x. So since it is x divided by 4, I can clear that 4 off by multiplying by 4 over 1. If I multiply by 4, 4 over 1 is the same as 4, right? This fraction is the same as 4. So if I multiply by 4, now the 4's disappear on the left. I'm sorry, on the right this time. But if I multiply by 4 over there, I got to multiply by 4 on the left side. So it is 4 times 1.2, which is equal to x. And 4 times 1.2 is 4.8. So x must be 4.8. All right. One more. Let's say we had 3/5 times x equals 1/4. All right, now we're getting a little somewhere. This one is a little more complicated because technically there's two things happening to x. You could consider it one thing, but really it's, if you wanted to get into the nitty-gritty, you could say it's also two things. This is 3 times x, and then that's being divided by 5. So x is being both multiplied by 3 and divided by 5. Now, collectively, if you multiply by 3 and divide by 5, that's the same as multiplying by 3 over 5. Multiplying by 3 over 5. So you ask yourself, what can I do to clear that 3/5 away from the x? I'm trying to isolate my x. We could, since it's being multiplied, right? It's 3/5 times x. You see I've got this little multiplication going on right here. I could divide by 3/5. Divide both sides by 3/5. However, there's an easier strategy here. We need to probably think about our easiest strategies when we're solving these because it helps us to solve the problems quicker. The easiest strategy is to say, well, what gets rid of the 3/5 the fastest? I could divide by 3/5. 3/5 divided by 3/5. Again, that would look like this. Divide by 3/5. And 3/5 divided by 3/5 would be 1. It goes away. I'll be left with 1x. However, I don't want to do that. And here's why. Because there's a faster way. Instead of dividing by 3/5, I'm going to multiply by 5/3. Because if I take 3/5 and I multiply by its reciprocal, 5/3, then the 5's cancel and the 3's cancel. And I'm left with just x. However, I just multiplied the left side of the equation by 5/3. I must multiply the right side of the equation by 5/3. You have to treat both sides equally. So if I do that, I multiply across. 1 times 5 is 5, and 4 times 3 is 12. Our answer, which we were not going to come up with mentally, is 5/12. So you can see this algorithm, this inverse operation strategy, helps us get to the answer quicker. All right? There are a few word problems, but I got to be honest, the word problems are very, very basic, and they're just reinforcement of the same concept. So I'm going to drop them out of the video because the video is already getting long. Hopefully this is enough. The homework doesn't go into any more detail than this sort of stuff. It's very basic right now, but we're going to build on this. This concept is wildly important. You got to make sure you understand at least this first process for solving what we call one-step equations. Each of these required one step for us to get to the answer. All right, that concludes this video. Thanks.